Okay, so we're going to get into chapter 11, section 3. Last time we left off doing this example 8 problem, and again we use dimensional analysis as we've always been doing in order to figure out the answer, and we're going to continue to do that. Section 3, dilutions and concentrations. The main thing here is if you have a starting solution that's more concentrated and you're adding, let's say, water to it, and that dilutes it. So you have an initial volume that's going to grow to a final volume that's going to be larger, and you have an initial concentration which is going to go down to a final volume, or I'm sorry, a final concentration which is smaller. And how do you calculate those final volume or final concentrations? We have right here something called the dilution formula, really easy formula. C1V1 equals C2V2, which you could also think of as C initial, volume initial, and C final, volume final. C is concentration, and as long as you're using consistent units, it could be anything. So those different concentrations that we had before, like molarity or molality, or even percent mass by mass or something like that, as long as you use it on the left side and on the right side, this formula will still work. Same thing with the volume. If I use milliliters here, then this one has to be milliliters as well. So you can't mix different units, but if you're consistent, it will work. So let's start off trying, first of all, this. Hang on, that just froze on me. Bring it back. There we go. Let's try doing this first example 9. It says 25.0 milliliters of a 2.19 molar solution are diluted. So diluted right there, keyword, I'm thinking dilution formula, which is, again, is this right away. They're diluted to 72.8 milliliters. So see, I'm starting with a small volume, I'm adding water, and I'm getting a final larger volume. That makes sense. It says, what's that final concentration? So I started with this concentration. What's the final? So I'm using the dilution formula. So let me, C1V1 equals C2V2. Let's fill in those numbers. The initial concentration, what am I starting with? That's the 2.19 molar. And the initial volume was 25.0 milliliters. The final concentration, C2, is what they asked me to figure out. And so we'll leave that as the variable. And the final volume, they said, was 72.8 milliliters. And again, consistent units, so I know my C2 is going to come out in molarity, just like that one is. At this point, all it is a math problem. Just plug it into the calculator. So let me pull that up here. And solving for C2, so I've got 2.19 times 25 divided by 72.8. So 0.752. So C2 equals 0.752. And again, units of molarity, because that's what we put in over here on the left side is molarity. Notice the concentration did go down as we predicted. The volume goes up, concentration goes down because we're diluting it, and so it seems like a reasonable answer. And it went down not greatly because we didn't increase the volume greatly, about a threefold, and so the concentration went down about threefold. I think that makes sense. Okay. Next, they've got this picture of a IV bag here, and kind of this problem. This is one of those little inserts, but it's a good problem to go through. It says if the stock solution is 10% potassium chloride and the final volume and concentration needed are 100 milliliters and 0.5%, then it is an easy calculation to determine how much stock solution to use. So what are they asking for? They're saying the stock is 10%. They gave me an initial concentration. They gave me a final concentration here and a final volume. They're asking me how much. In other words, what is the initial volume that I should use? And something like that. But again, that's just a dilution formula. So C1V1, C2V2. Same equation as before. Concentration was 10% over here that I'm starting with, but I don't know how much I'm going to grab initially. But the final, I need it to be a 0.5%, and the final volume, I need it to be 100 milliliters. So again, percent and percent there. I don't even know if that's a percent mass by mass, volume by volume. It doesn't matter as long as I have consistent units, which I do here. This one's milliliters, so I know my V1 will also come out in terms of milliliters. In fact, I could write that unit in right now and pull up our calculator and punch those numbers through. So let's give that a try, solving for V1. So I've got 0.50 times 100 and then divided by 10. And so the answer there is 5 milliliters. I guess with significant digits I should put 5.0. So an initial 5 milliliters of that more concentrated IV solution diluted up to 100 milliliters would give me both the right volume and the right concentration. Okay. And that's it. The whole entire section there. And here's the book. The whole section here is all about just that one formula. I don't even see where they're using. There it is. Their formula in the book uses M for molarity, I think. I use C instead, C1V1, C2, because, again, as long as you have the same unit of concentration, it's going to work. It doesn't have to be just molarity. And so I represent that a little bit different than the book does. Okay, so we're done there. That's a short section. Let's go back. Moving on. Section 4, concentration as conversions. I don't know why they have a totally separate section for this, really. It's the same sort of calculation. You're setting it up with dimensional analysis, getting the units to cancel correctly. Concentrations, usually in terms of molarity, so moles per liter, I can convert between moles and liters, in other words, by using whatever concentration is given. So there's really nothing new here at all. Let's just jump into a problem. You'll see what I mean here. Example 10 from the textbook. Using concentration as a conversion factor. So again, whatever. How many liters, here's the real question, how many liters of 2.35 molar copper sulfate, so again, it gave me a concentration, are needed to obtain 4.88 moles? Notice that's not a concentration, that's just an amount. It's like grams or moles or dozens, right? Just an amount of this copper sulfate. All right, so if I'm going to set this up using dimensional analysis, like I've told you before, take those concentrations that they're giving you and interpret it first. If I interpret that, that means 2.35 moles of copper sulfate per 1 liter of solution. That's what that capital M means again. And now that I see that interpretation, I can use it in my calculation. All right, so let's try that. We're trying to obtain 4.88 moles of copper sulfate. So that's where our calculation begins. 4.88 moles copper sulfate. And now we set it up so that things will cancel. Moles is on top here, so let's put moles of copper sulfate here on the bottom. I'm going to convert that. Here's my conversion right here. It's from moles to liters. It tells me what those numbers are and everything, so I can go to liters of the solution, and those are my numbers. Notice the 2.35 is by the moles of copper sulfate, so I do the same thing here, 2.35, which happens to be on the bottom. But again, it's only there because I placed it there purposefully so that things would cancel correctly. Let's go ahead and cancel that right there. That will tell me how many liters of solution, and that's exactly what they've asked me for, how many liters of that solution are needed. So this is a one-step conversion. My units are liters of solution, and now I can pick up my calculator and punch those numbers through. And so let's give that a try. 4.88 times 1 divided by 2.35. And so there's my answer, 2.08. 2.08 liters of solution. So that's how much I would have to grab, like a 2-liter bottle of soda, right? 2 liters, 2.08 liters would give me the correct number of moles, that is to say 4.88 moles of copper sulfate. So this is what the section is talking about. They're using concentrations as conversions. Here I'm converting moles of copper sulfate to liters of that solution. Does it need its own section? Probably not, but that's how you would do that kind of a problem. The key, as I've said many times, is to interpret what they mean when they give you that concentration. Don't just leave it as a capital M or percent M by M or whatever it is. interpret it instead. Write it out to say what it really means, and then you can use it in your calculation. Let's try the next one. Example 11. What mass of solute is present in 0.765 liters of 1.93 molar sodium hydroxide? So identify what is the solute. It's the sodium hydroxide. This solution, they put so much sodium hydroxide into water to reach that concentration. We've got that volume, right? And so, yeah, water is the solvent. Sodium hydroxide is this solute that they've dissolved into it. And they're asking us for the mass. How much do we actually have to get the mass of how much solute do we sprinkle in and dissolve in order to achieve that solution? Once again, I'm going to start by looking at that solution and saying, hey, what does that really mean? That means 1.93 moles of sodium hydroxide per 1 liter of the solution. And now I can use that in my calculation. What do I start with? Well, we've got 0.765 liters. That's the amount of solution that we have, and we're going to convert that essentially to the moles of the solute. So let's start there. 0.765 liters of that solution. Set it up so things cancel, so liters of solution on the bottom. And what can I convert it to? Moles there. Moles of sodium hydroxide. Numbers there. Looks like the 1.93 is by the moles, so that goes on the top this time. To a 1 liter solution. Boom, those are gone. And so now in my calculation, I've made it to moles of sodium hydroxide. They don't want me to stop there. They want mass. In other words, grams. So my next step, I'd have to convert from moles to grams of sodium hydroxide. And moles to grams, well, that's off the periodic table. And so I should be able to go ahead and grab that. Let's see. Periodic table here, sodium hydroxide. You can add them up off the periodic table, or you can just use a program like this. Oops, I gotta hit that. There we go. Same thing if you would add it up, 39.997. So let's go ahead and use that. Got my mouse tangled up in a wire there. Okay, 39.997 grams per mole. Moles and moles cancel. Now I've got grams of sodium hydroxide, and I can pick up my calculator and push that through. All right, 0.765 times 1.93 times 39.997 equals 59.1. 59.1 grams. All right, so just to back up and recap there, we're trying to make that volume of that concentration solution. They're saying how much of the sodium hydroxide, the solute, do I have to weigh out to do that? And we just did the calculation. It turns out to be 59.1 grams of it. Okay. Example 13. This looks like a long problem. This is a little, probably the most challenging one in this lot. I don't know, 13 and 14 about the same. They're just a little bit longer, but you've seen everything in previous chapters to do this. So let me step you through it. Let's read it first. A student takes precisely measured sample called an aliquot. An aliquot is just a little teeny sample, maybe from a larger one. And so, you know, if I've got a bucket of stuff and I just take a little sample out of it, they'd call that an aliquot. All right, so that's what that word is, no big deal. So they got a sample of 10 milliliters of a solution of iron 3 chloride. They took 10 milliliters out, so that's the volume. The student then carefully adds 0.1074 molar sodium oxalate. That's C2O4, that's oxalate. We don't use that one a whole lot. But they add it until all of the iron 3 has precipitated as iron oxalate, iron 3 oxalate. So he's doing a reaction with this. We're starting with what was in the solution in the aliquot there, iron 3 chloride, adding sodium oxalate. So we get this reaction. Here's the arrow, and here's our precipitate, the solid that comes out. and the sodium chloride. That's just a double displacement reaction, again, from past chapters. And this is really nice. They balanced it for me. Whenever you have a reaction and you're going to do some kind of calculation, you got to make sure you have a balanced reaction, balanced equation. And they've done that for us. All right. Then it says, using a precisely measured tube called a burette, the student finds that 9.04 milliliters of this sodium oxalate solution was added to completely precipitate the iron. What was the concentration of that original iron 3 chloride in the original solution? It says this is called a titration, basically. So lots happened here. A lot of numbers are given here. And I'll put my camera. There we go. Let's try it. Here's the equation. I'm just going to write it out a little bit larger. Plus sodium oxalate. Make sure it stays balanced. C2O4, 3. Here's my solid. There's my precipitate that they're talking about. And 6 sodium chlorides. Okay. As usual, I like to write underneath my balanced equation what it is they're talking about. And so we have this initial 10 milliliters of the iron 3 chloride. That's over here. So 10 milliliters of that stuff. A student carefully adds 0.1074 molar sodium carbonate. So that's here, oxalate, right here. That's the concentration they're giving us. Let's go ahead and write it right underneath. That was the concentration of it until everything's precipitated. So adding enough of this to draw out all of this iron and have it precipitate as this product here, iron oxalate. It says using that defines that 9.04 milliliters of that sodium oxalate solution was required. So again, that's this solution here, 9.04 milliliters. What was the concentration of that original solution? So question mark here, molarity, that's what they're asking us to calculate. All right, and let's see, did I miss anything? Nope, that's all of the numbers and everything they gave me. So look, we're starting with a known here. They're asking us about something else in that same reaction. We have a balanced equation. This is a stoichiometry reaction, but it's done in the solution phase. It's done as things dissolved in water, essentially. So we have to use stoichiometry along with the idea of concentrations. Okay, first of all, these milliliters, we work in terms of liters if we're doing molarity, because here it is, molarity is moles per liter. And so I'm going to cross that off and write that as a liter, 0.00904 liters. Just move the decimal 3 spots. Same thing here, this 10 milliliters, that's the same thing as 0.010 liters. Right. Just trying to get my units in order. Also, this molarity here, keep in mind that's moles per liter. Not a lot of room to write that, but let me just put it over here. That's the same thing as 0.1074 moles of that solute, which in this case is sodium oxalate, per 1 liter of the solution. And we're going to probably need that. Okay. What do I start this calculation off with? I don't start off with a conversion step. And these molarities are essentially conversion steps because we've got moles and liters. I can go back and forth. No, I would start it off with an actual quantity, an amount that I have, which in this case, I've got this here, and I got this here. Well, this is my unknown. This is what I don't know about necessarily. But this is the one that I do know exactly how much I've used. So, I think this is the one to start off with. Start off with what you know. As always, I always like to say that. And so I started off with 0.00904 liters of my sodium oxalate solution. Okay, in all stoichiometry reactions, the first step is to convert it to moles. And I can do that using the concentration of the solution. Remember, this is 0.00904 It's supposed to be a 4 there, is referring to my sodium oxalate solution, this guy right here. And so I can go from liters of sodium oxalate to moles of sodium oxalate, because I know right there its concentration, again, of this guy, 0.1074. I know what that conversion is there because they gave me the concentration, 0.1074. Liters and liters cancel. So now that I've made it to moles, I can use my balanced equation to go from one species to anything else in that reaction. In this case, I want to go over to the iron 3 chloride. That's what they asked me about. So that's my step here, moles of sodium oxalate to moles of iron 3 chloride. And for my balanced equation, looks like I have a 3 on the sodium oxalate and a 2 on my iron 3 chloride. So that cancels. So now I've got moles of iron 3 chloride. I'm going to put an equal sign right there. That will tell me exactly how many moles of iron 3 chloride was in that solution. And let's pick up our calculator and punch that through. 0.904 times 0.1074 times 2 divided by 3. Okay, there we go. 647 times 10 to the minus 3, or in other words, 6.47 times 10 to the minus 4. 6.47 10 to the minus 4 moles of iron 3 chloride. That's almost what they asked me for. They asked me for what was the concentration of that solution. Well, I've got how many moles were in that solution, and over here I do have the volume. Concentration, units of molarity, would be moles per volume, moles per liter, I should say. So moles divided by liters. So the concentration will equal 6.47 times 10 to the minus 4 moles of that iron 3 chloride per, and the volume was 0.010 liters. So I go ahead and divide that. So that number there divided by 0.010 equals 64.7, and times 10 to the minus 3, that means milli. And so while this is going to come out in terms of molarity, it could be in millimolarity as well. But, well, let's write them both. 64.7 negative 3, that'd be 0.0647. 0.0647 molar. Or, like I said, that could also be represented as 64.7 millimolar. And there we go. That would be the solution. The answer, I should say. Alright, so this is a longer problem. They're asking me for what was the initial concentration here. And we figured out the moles. They told us the volume. We divide. We get the initial concentration. So hopefully you can see it's an application of everything that we've been doing in many chapters, kind of all coming together now to do that sort of a calculation. Let's try 14. It's going to be the same kind of a thing. H2O2, which is hydrogen peroxide. You can pour it on wounds, bubbles up, kills things, kills good antibiotic like that. H2O2 is used to determine the amount of manganese. That is right there on the periodic table, number 25. Don't confuse that. Let me put that back up. Don't confuse manganese with magnesium, which is over here, Mg. They're talking about this one right here. Okay. So you could use hydrogen peroxide to determine how much manganese according to this reaction. So you got so much manganese in there. It's in the form of MnO4. It reacts with hydrogen peroxide to give you those products. It reacts in a 5:2 ratio. There's my balanced equation. What mass of a 3% peroxide solution is needed to react with that? Okay. So again, this is a stoichiometry problem in solutions. Let's write it out, identify what they really mean by things, and then see if we can make those units cancel. Take a second to rewrite this. That's called permanganate, by the way, MnO4. one of those, we don't use it a whole lot, but it shows up now and then. There's my peroxide. 6 H pluses. Those H pluses probably came from some acid like hydrochloric acid, so this is in an acidic environment, is what that tells me. It's not going to be necessary to actually do the calculations here. It's producing O2 gas, so that's my bubbling that I expect to get when peroxide reacts with something. And water is actually a product as well. Okay, so there's my balanced equation. Let's see. What mass of peroxide? So question mark here. What mass? How many grams do we need there? How many grams? What mass of a 3 concentration, 3% mass solution? So the concentration is 3.00% mass by mass. That's my concentration. We're going to have to interpret that and say, what does that really mean? All right, is needed to react with 0.355 moles of this permanganate. So over here, this one is 0.355 moles. All right. This is what I know. That's how much is reacted. It reacts with this solution, and they're asking me how many grams of that solution. Maybe I should add that. How many grams of the solution, mass of the solution. That's what they're asking me for. I've got a concentration here. Let's go ahead and interpret what that means. This means, this is a percent by mass, so that means 3.00 grams of the solute, H2O2, per, and this is a percent, so that means per 100%, so 100 grams of the solution. So now I can use that as a conversion to go between grams of peroxide and grams of the solution. And that should be pretty much everything I need now to solve this problem. Start with what you know. 0.355 moles of MnO4 permanganate. Alright, in any stoichiometry, first thing, convert to moles. They gave me moles. That was nice. So I don't have to convert. I can go right to my from species to species stoichiometry in the balanced reaction, which in this case, moles of permanganate. Get that on the bottom so it cancels. And I'm interested in going to the peroxide H2O2. So moles of H2O2 on the top. And for my balanced equation, that's a 2 and a 5. So those are gone. At this point, I've got moles of peroxide. They want grams, though, and they gave me this concentration in terms of grams of peroxide, so that's my next step. Convert from moles to grams. Moles of H2O2, grams of H2O2. And to do that, grams per mole, I'm going to have to look at the periodic table and get the numbers off there. 2 hydrogens and 2 oxygens. So you can add that up, like I said, or use a calculator, and that's what I'm going to do here. H2O2, hydrogen peroxide, and they're just adding it up from the periodic table. 34.01, I'm sorry, 34.0147. Okay, 34.0147 grams per mole, and top and bottom moles of peroxide cancel. So now I've got grams. That's how many grams of peroxide I need, but it comes in this solution form, a 3% solution. You know, like you could buy that at HEB or something like that. It comes in a brown bottle usually. 3% sounds about right of what you'd find in the store. But I can use this again to convert. I can convert between grams of just the peroxide and grams of the solution, and that's what they are asking for, how many grams of the solution. So perfect. Put this on the bottom so it cancels. H2O2, grams of the solution will go on top, and there's my numbers. Again, they were hidden in this concentration that they gave me. So 3.00 grams peroxide for every 100 grams of the solution. That cancels, and I finally have what they've asked me for. I can put the equal sign, put the units, and pull up my calculator, punch it through. So let's do that. 0.355 times 5 divided by 2 times 34.0147 times 100 divided by 3 equals, there we go, 1006 times 10 to the third. So in other words, 1006. 1006 grams, which would be the same as 1.006 kilograms of that solution. Okay, so like I said, those are probably some of the tougher problems that we've seen, just because there's a lot happening there. But the idea of calculating, getting the units to cancel, using a balanced equation is everything that we've been using before in this class. All right, let's move on. The next two sections, sections 5 and 6, they keep them separate in the textbook. Not sure why. They really just kind of go together, and I'm going to just treat it that way. Colligative properties. Now, colligative properties are those type of properties that it does not depend on what you're talking about, what the identity of the stuff is. It only depends on how much you have. So you could use anything, well, anything within the same category. But the property doesn't depend on what it is, just how much. I mean, for example, they throw ice to melt, they threw salt, excuse me, on ice to melt it in the wintertime. It doesn't matter which salt you choose. You could choose, remember, salt is an ionic compound. You could choose any of the thousands that are out there, so you just might as well just choose the cheapest one, because they're all going to do the same thing and cause that ice to melt. So that would be an example of a colligative property. The identity doesn't matter, just how much do you actually throw out there will melt so much ice. And that's what we're talking about. Now, there are 4 basic colligative properties that people will typically often use. They go through those in this textbook too much. We're going to skip 3 of them. We're only going to talk about 1 of them. So, freezing point depression, boiling point elevation, and Raoult's law with vapor pressure. We've talked about freezing point and boiling point, and we've talked about vapor pressure, but colligative properties, you can get those freezing points or boiling points to actually change, to go up or down slightly. I mean, that's how we get the ice to melt, truthfully. And there's equations and ways to calculate what the new boiling point or what the new melted point would be. And so those turn out to be colligative properties, but you can skip those sections. I'm not going to ask it on the quiz. But the one that is kind of important for health sciences and biological systems is the 4th one, osmosis. And we can do calculations with osmosis as well. And it's colligative, and so it doesn't matter what, just how much. So osmosis is, by definition, the passage of a solvent, not the solute here, but a solvent, okay? The passage of a solvent through a semi-permeable membrane. Like your cell membranes, they're semi-permeable. And the solvent that they live in is water. And so in that case, we're talking about the passage of water through this bilayer that we call the cell membrane. Now again, it technically doesn't have to be a cell. It could be any permeable, semi-permeable membrane. It doesn't have to be water, right? But yeah, in the context of cells and living things, it's water and membranes that we're talking about. Let's see, why does this actually occur? Picture this kind of an experimental setup here, where we have a beaker. It's divided in half by a semi-permeable membrane. And on one side, we put a 0.1 molar solution of something, and over on this right side, a 1 molar solution. So on the right side, it's 10 times more concentrated than the left side. Now notice the book doesn't even tell you what the solution is, because again, that's not important for colligative property. Maybe it's a sugar solution, maybe it's salt water, maybe it's glucose. I mean, whatever it is, it doesn't matter what, it's just how much. And how much is, they did tell us, right? 0.1 molar here, 1.0 molar here. So this is 10 times more concentrated than the left side. What's going to happen? The semi-permeable membrane allows the solvent, water, to pass through, but it doesn't allow the other stuff to pass through, whatever this solution is made of, the solute. It's kind of like a fishing net. The little minnows can go right through, but the big fish can't because they're too big. Exactly the same idea here. So the water can pass, but the other stuff can't. And so you set this up, you give it a little time. This is the result that you would see. The actual level of the solution on the right side would go up, and this one will go down. Why? Because imagine this beaker, you put this on the left and you put this on the right, and then you take away the membrane. What would happen? Well, the solutions would mix together and mix until it was uniform. It was homogeneous throughout the whole beaker. The same thing's trying to happen with that membrane still in place. The trouble is the big things can't cross the membrane. The big fish can't go across the net again. Only the water can. And so to try to make it as uniform as possible, what this system does is it allows the water to cross, trying to dilute the more concentrated side. It always goes in that direction. So if I was to draw that on this diagram here, I would say, hey, the water, the H2O, is going from the left to the right, trying to dilute that right side. As it leaves the left side, that would actually make it more concentrated over here, and as it enters the right side, it would dilute it, making it less concentrated. So this one goes down. I'm sorry, this one goes up. It goes down in volume. It goes up in concentration. This one goes up in volume, but down in concentration. And it would, ideally, anyway, keep going and keep going and keep going until the concentrations were the same, and we would have it homogeneous. Now, in reality, as this happens, you've got a stronger pull of gravity now on the right side, and so it only goes so far, and then gravity is fighting it, and but it's still going to be closer in concentration and therefore more homogeneous throughout that beaker than in the initial. So that's why it happens. The water crosses the membrane. This is key again. The water crosses the membrane until, or in the direction, I should say, of trying to dilute the more concentrated side. And if there's nothing else fighting it like gravity, it will keep doing that until they're the same on both sides. All right. The height of the water of the one side compared to the other is called the osmotic pressure. It's a pressure because it's kind of like the same as if you were putting pressure down on this left side, squeezing it, if you will, forcing the water to go over to the right side and therefore up. It's like, how much pressure would you have to put on that left side to make that height difference? How much pressure? How much would you have to push down? So it is a pressure. And it's the pressure due to osmosis. So that is the osmotic pressure. And they use a capital pi to represent that. Instead of M for mass or V for volume, pi for osmotic pressure. Okay. The equation that you could use to calculate how much osmotic pressure is needed is right here. Pi equals I m RT. T is temperature. It's got to be in Kelvin, just like in the gas laws. It's got to be Kelvin. R is the ideal gas law constant, which is the same one we used before. And typically we're going to use 0.08205 liter atmospheres per mole Kelvin. But again, if you're using a different pressure instead of atmospheres, if you're using bars or torrs, well, you could use the corresponding value for R. For these calculations, we're probably just going to stick to this one for the most part and just leave it in atmospheres. But again, questions might give it differently, in which case go find the right value of R. M is the concentration. M is the molarity, then, of the solution that you're trying to measure the osmotic pressure of. And I is called the Van Hoff factor. It's essentially equal to the number of pieces that solute breaks up into when it dissolves. Okay, so for example, if I dissolve sodium chloride, scroll over here a little bit here. If I dissolve sodium chloride in solution, that's an ionic compound. When you put it in water, it breaks up into sodium plus and chloride minus. So there's two pieces, so I would equal 2. Just that simple. Sugar, like glucose, blood sugar, that's a covalent molecule. When it dissolves, it stays together. It's not ionic, so it stays together, and so it produces just one piece, and therefore its Van Hoff factor is 1. Here's another ionic calcium chloride, ionic compound. When it dissolves, you're going to get a Ca2+ and a couple chlorides. That's a grand total of 3 pieces. So its Van Hoff factor is 3. So how many pieces it breaks up into. Now, why is that important? Because osmosis is a colligative property. It doesn't care what the thing is, just how much is there. So in this case, this concentration right here in the osmotic pressure equation is looking at the total molarity of stuff. It doesn't care if they're calcium 2 pluses, or if they're chlorides, or if they're sugars. It doesn't care. It just wants to know what the grand total is. And so we need to know how many pieces something will break up into in order to calculate that. All right. Here's their little table of Van Hoff factors, and again, you can go through here and you see that it simply equals the number of pieces that these various ionic compounds would break up to. All right, so let's try this problem here. What is the osmotic pressure? So what are they asking me for? They're asking me for pi. Pi equals IMRT. I know that's the equation for osmotic pressure. So what is pi of a 0.33 molar solution of C6H12O6? Now that is glucose, that's blood sugar, and for that it's a covalent molecule. It does not break up, and so I equals 1. Notice they give me 25 degrees Celsius. I'm going to have to plug in temperature, but I've got to convert that to Kelvin. That's 298 Kelvin. Remember, that's you just add 273 in order to convert Celsius to Kelvin. So I think I've got everything I need. This would equal 1 times the concentration, 0.333, times R, which is 0.08205. This is molarity. This would be liter atmospheres per mole Kelvin. And then temperature, 298 Kelvin. Notice, let me put this in red, notice the units. Kelvins and kelvins cancel there. I've got liters per mole, and here I've got moles per liter. So that's a 1 over m. This is an m, so that cancels. And I'm left with just atmospheres. And so when I put my equal sign, the unit is atmospheres, which is pressure, and that makes sense since I'm solving for osmotic pressure. Okay, let's get the calculator, plug this through, and see what the answer is. Got 1 times 0.333 times 0.08205 times 298. 8.14. So if I had a solution, that concentration of sugar, it would be able to exert 8.14 atmospheres of osmotic pressure. Again, that's how much it would be able to push over, if you will, into something else, and that's how much pressure, the equivalent of pressure, you would have. They didn't ask this, but as a follow-up, what if instead of this glucose, this sugar, the solute was sodium chloride? I thought that would be interesting to follow up on and just do. Well, sodium chloride, the I equals 2 because that's ionic, and when it breaks up, you can have Na plus and Cl minus, and so you'll have 2 pieces, so I equals 2. So 2, that's my I. Concentration was 0.333 molar. Everything else is the same. 205 for R, 298. So everything else is the same except I've got a 2 there. And so instead of a 1, I'd have a 2. Get my calculator. Just multiply that by 2, in other words, this time. And it would be 16.3. 16.3 atmospheres. So if I made the same kind of a solution but using sodium chloride instead of sugar, it would actually double the osmotic pressure because of the number of pieces that sodium chloride breaks up into. Okay, this turns out to be really, really important for IV solutions and for biological solvents and solutions like in the cell or in the blood or in the body, because we don't want, we want to avoid. We don't want a lot of water passing across all of these semi-permeable membranes in our bodies, which are called cell membranes. Because if too much water passes across them, it's going to affect the cells greatly. For example, if I take, here's the picture from the textbook, if I take red blood cells, RBLs here they are, they're floating around in the blood. Remember, blood is essentially water, but it's got all this other stuff dissolved into it, so it's got a total concentration of stuff as far as osmotic pressure. All right? And if it is the same on the inside versus the outside of the cell, the total concentration of stuff, then that's like this picture up here, where it's the same, well, this picture here, where it's the same, where I'm not going to have anything going left or right because they're the same concentration, and so the cells, they'll be intact, they'll be happy. There's no reason water would cross either in or out of them. If you put those cells in a solution that has less stuff concentrated in it, and so that's this middle picture, then the water is going to, remember the key, the water is going to cross the membrane trying to dilute the higher side. And so it would cross into these cells trying to literally dilute the stuff inside the cells. And be like a water balloon where you just put more water in and more water and more water, and eventually those cells can only hold so much, and they would burst wide open, and they're showing that right here, that these cells bursting. And so that's certainly no good. You don't want to have your cells bursting open. That would be fatal. The opposite side, what if you put those cells into a solution that was really highly concentrated? Then you'd have the water, again, trying to dilute the more concentrated side, and so the water would be flowing out of the cells, trying to dilute the environment, trying to dilute what's out there, and so the water would flow out, and you'd get these cells shrinking like raisins. They would shrink and shrink and shrink, and that's called crenation, right? And so it's really important. We don't want either of these two things happening. We want them to stay healthy like this. The definitions here, the words that you need to know, are isotonic, hypotonic, or hypertonic. Iso, remember, iso means the same. Again, like an isosceles triangle in elementary school, that it means a triangle with two sides that are the same length. Iso means the same. So isotonic, that's what we want. We want the outside of the cell to be the same concentration as the inside of the cell, like in this picture here. The outside and the inside are the same, and so you're not going to get water doing a net flow either direction. Right? In other words, in your blood, the total concentration of stuff just out in the plasma part, the liquid part of the blood, right, is the same as the concentration of stuff inside your red blood cells. They're the same. If they weren't the same, then you'd have water flowing in one direction or the other. But no, we don't want that. So your body actually works very hard to keep it the same. You need those electrolytes, you need the sugar, you need all that stuff that's dissolved in blood. It's going to match what's inside the cell, the cytosol of the cell. And if it matches, we'll call that an isotonic solution, and your red blood cells will be happy. This middle picture, a hypotonic environment. So hypo means low or lower of. Like if you go outside when it's really, really cold with no coat on, you can get hypothermia. Your body temperature gets too low. Hypo means below or low. And so here you're putting the red blood cell into a solution that has less stuff dissolved. So the water will go into the cells trying to dilute it, and again, they will swell and they will burst open. You'll get cell lysis occurring here, the bursting open of cells, and again, that's not good. Hypertonic, hyper, like hyperactive. Hyper means above or bigger than, right? And so here you're putting the cells into a solution which has all kinds of stuff dissolved into it, and so the water goes out of the cell trying to dilute it, and the cells shrivel up, so they crenate hypertonic solutions. So those words describe the environment, the solution, if you will, that you're putting the cell into. It's either iso, hypo, or hypertonic. And we can use the equation up there with pi equals IMRT, to calculate, truthfully, what is the osmotic pressure on the inside of the cell, what is the osmotic pressure on the outside of the cell, and we want those numbers to be the same. If they're the same, then they will be happy little cells. What are those numbers? Well, let's see. In the blood, it turns out to be about 0.300 molarity. You'll see this term too, OS molarity. That means osmolarity. That just means that we have not cared what it is. We're just taking the grand total concentration because it's a colligative property. So it's 0.300. If you made a solution using just sodium chloride, So it's not all this other stuff like sugars and potassiums and calciums and chlorides. No, if you used, like just in the lab in a test tube and made a solution just using sodium chloride, it would turn out to be 0.9%. 0.9%, it's weight by volume, but anyway, 0.9% solution of sodium chloride. In other words, 0.9 grams of sodium chloride per 100 milliliters of water. That solution there is the same, it would be isotonic, with 0.300 osmolarity, which is again what these cells are at. So 0.9%. If you did it with dextrose, dextrose is again an older name for glucose. It's still used once in a while, but anyway, dextrose, so it's blood sugar, just like glucose is. It's the same thing, just a different name. 5% solution turns out to be isotonic with it. So when you go to the hospital and they hook you up to the IV and they hang that IV bag up there, that's not pure water in that IV bag. If that were pure water, that pure water would go into your veins, diluting the veins. It would create a hypotonic environment, which is what you got here. That hypotonic environment would cause your red blood cells in your blood to swell and burst open, and yeah, it would be fatal for you. So it is definitely not pure water they hang in those bags. It's a solution. It's a solution of something. It doesn't matter what it is, colligative property, right? So, but it's a solution of something which is isotonic with your red blood cell cytosol. These are two common ones they use. They call this D5W. That's dextrose, 5% water. Well, yep, that's isotonic with the red blood cells. Right? Or, like I said, a 0.9% sodium chloride solution. That'll work too. Right? Those will keep your red blood cells happy. If they did not use that, then your cells are going to be bursting open and you will be dying. Okay, so there you go. That is the end of chapter 11. Lots of practice problems as usual online, and at the end of each section and at the end of the chapter, and that's it. Do the homework, do the quiz, and I'll see you on Monday.